this on chapter 11?
I think we're on 12.
I'm trying to find
Okay. Anyways, so what we're doing, if it has this efficiency, what does efficiency mean? It means what over what? Work out over energy in, right? So what happens when you lift this crate, the lifting is which one? Work out or energy in? Work out, right? And if you lift this high, then we know how much work was done. Also, we know that, let's see, what's a way to do this? Yeah, actually, I can't think of an easy way. We have to use this, and then we have to use the fact that work out equals QH minus QC, because QC is going to be the big deal. Because remember, when we say energy in, that's like QH. Okay? So what we have to do is we have to, that's what we have to do. We could solve this one for QH. QH is equal to WO minus QC, and then plug it in here. So we get WO over WO minus QC. And then we can solve this for QC. Right, so then we get QC is equal to WO over E. Oh, nuts. I've got to flip around the negatives. Yeah, it should be WO minus WO over E. Let me go through the algebra. I don't want to confuse people. All right, so first what I'll do is I would flip this, so I get WO minus QC equals WO over E. Right, and then I'll move this stuff around so that I can get QC is equal to WO minus WO over E. Isn't that going to be less than 1? It's going to be negative. That's interesting. That's going to be a negative number, isn't it? Does that make sense? I forgot to do what? This is supposed to be a positive? This is supposed to be a positive? Oh, yeah. Oh, yeah, there you go. Thank you. That's supposed to be a positive, which means this is a positive, which means that's a positive, which means that's a positive? Okay. Yeah, QC. Yeah, okay. Yes, question? Thanks, Sal. Yeah. Because energy in means like however you put it, right? It could be like liquid energy in, it could be solar energy in, it could be heat in, right?
So it's just like whatever it is.
Yeah. And because they're asking about the heat lost, then I said, okay, this is something like that. Yeah.
It's negative workout.
Negative workout?
Minus workout.
Negative workout plus workout.
Workout over efficiency minus workout.
So then this becomes, so this becomes this minus that. There we go. Good. Okay, is everybody cool with that? There you go. That's our final, my final answer. So then the workout, of course, is going to be force times distance, or in this case, Fw times h, which will give you 3,600 joules. So we get 3,600, I guess if you want, you can be clever and say this is work out times 1 over E minus 1. And so that's 3,600 joules times 1 over 0.75 minus 1. And since 0.75 is 3/4, 1 over that is 4/3. 4/3 minus 1 is 1/3. So our answer should be 1200 joules. Okay, so they move this slowly so that the thing, the steel thing, as it got heat, it just let the heat go into the environment. That's how that part works. Now the second part of the question says, what if it's raised quickly and the winch has, the mass of the winch is 2 kilograms and the delta T is 0.25 Celsius degrees. How much heat is transferred to the surroundings during this lifting? All right, so we already know that based on the efficiency, 1200 joules is going to be lost to the environment. Does that make sense to everyone? So all we have to do is find out how much heat, actually, you know what, all we have to do is find out how much of that heat was stayed in the block of the metal thing. So that's just going to be Q is equal to MC delta T. And then we will just take that and subtract it from this. Right? So what we're going to get is, I don't know, like we could say QC2 is going to be equal to QC minus Q. Do you get what I'm doing there? No. I'm saying this QC right here, because this is actually QC, right? That is the amount of heat lost, the amount of whatever, like the person is putting in energy lifting this crate. Part of their energy was lost as heat into the environment. Based on the efficiency and the amount of work done, that must have been, you must have lost 1200 joules. Now, the second time around, because you went faster, it just means some of the heat stayed in the pulley. Okay, so, but that doesn't change the efficiency. So you still only lost 1200 joules, right? But this time, some of this 1200 stuck in the pulley, and that's this Q right here. That's this Q right there. All right, so once again over here, in case you didn't see that. Yes. So this 1200 joules right here, that 1200 is the amount of energy that you lost. You can't help it. There's no way to make that better because that, there you go. Because this is 75%. Okay, that 75% doesn't change whether you pull fast or slow. So then this 1200 is how much you're going to lose. In part A, it all goes into the air. In part B, they tell us that part of it stays in the pulley. And they tell us the mass of the pulley, and they tell us the delta T of the pulley. Well, if I tell you the pulley is steel, and I tell you it's mass, and I tell you it's changing temperature, can you not tell me how much heat was put into it? That Q is MC delta T, that's it. So that's how much heat is left in the pulley. I just subtracted from 1200 and I get my answer. So what is the specific heat capacity of steel? Did anybody do this problem?
Do you have to like know this specific?
It's in your book.
Oh,
Okay. Okay, you should know this from your notes. As I mentioned in the beginning of the year, when there is a table, you should note that in your notes. What is it?
wait, is it perfect?
What is it?
What number? So,
I don't know. 450? Okay, so whatever, we'll just use that. So if we use 450 here, then we get the mass, which is 2 times 450, which is 900 times 0.25, which gives us 225. So then we're going to subtract 225 from 1200, which gives us, is that 975? Yeah. 975 joules. See, so 975 joules. So over here, we take our 1200 and we subtract the 250 that comes from here, and we end up with 975. Wait, 250? I think 250, that's 225. Right? 225?
225.
How many?
Yeah, they just do that.
You just play the songs that I've heard.
No, it's hitting his face.
The red one had stuff in here, I think.
But didn't they used to make those in metal?
I know. I remember they were plastic when I was a kid.
Are they plastic still?
Because that toy was like from when I was a kid. That's when it came out. That's why I thought it was so cool when my wife bought it. And then I played it and I'm like, hey, this isn't as cool as I remembered. Okay, questions on 29? Wow, that's been recording the whole time. Awesome.